Hello friends, so in this video we will talk about deterministic finite automata or DFA. So DFA is a finite automata in which from each and every state on every input symbol exactly one transition should exist. So let's understand this with the help of an example. So suppose we have one finite automata having initial state q0 and the final state q1, and we have the transition from q0 to q1 on A and q1 to q0 on B, and suppose our input alphabet is A comma B. So what it is saying, the DFA is from each state on each input symbol exactly one transition should exist. So is this automata DFA? So first we'll find that if it is finite automata. Yes, because we have the finite number of states and we have the finite number of transitions between them. So this automata is finite automata. Now let's find out if it is deterministic finite automata or not. Right, so here on this state q0 we have the transition on A but we don't have transition on B, so this is not the DFA. Suppose we make one transition on B, so here from this state q0 we have exactly one transition on A, exactly one transition on B, so this is fine. But on q1 we have exactly one transition on B but we don't have any transition on A, so this is again not DFA. Suppose we have A here, so now we can see that we have exactly one A, exactly one B transition on q0, exactly one A and exactly one B transition on q1, so this is now DFA. Suppose now we have another this transition from q0 q1 to q0 on A, so is it DFA now? So q0 is fine because we have exactly one transition on A and B, but here on q1 we have exactly one transition on B but we have two transitions on A, so this is again not DFA. So we should have exactly one transition on each input symbol. Suppose the input alphabet is A comma B comma C, so is this DFA? Suppose we are removing this transition, so we have AB on q0 and AB exactly one AB on q1, so is this DFA now? No, because our input alphabet is now A, B and C, so where is the C transition from q0 on q1? So if we have C transition also from q1 and q0 and q1, then this is DFA. So it will depend on the input alphabet, it is DFA or not. So from each symbol of the input alphabet we should have exactly one transition from every state, right? So this is DFA. Now let's see the formal definition of DFA. So DFA is Q, sigma, Q0, F and delta. So Q is the finite number of states, we know that because this is the requirement for FA. Now we have sigma is input alphabet, q0 is initial state, so we should have exactly one initial state in DFA, and the F is set of final states, so this can be 0 or more, so we can have DFA with no final states, this is not a problem. And then we have transition function, so it is saying that from each state on each input symbol we should go to exactly one state. So these four are the requirement for finite automata. This delta is specific to the DFA. So for all the finite automata, DFA, NFA and epsilon NFA, these four things will be same, only delta will change. So now we will find out if these automatas are DFA or not. So let's see. So here we can see that we have finite number of states and the input alphabet is AB for all these automata. We can see that in all automata we have exactly one initial state, so this is also fine. And this set of final, so we have here we have one final state, here we don't have final state, here two final states, here one final state. So all these four parameters are satisfied by all these automatas. Let's find out the most important one, that from each state on each input symbol if you are going to exactly one state or not. So here on A we have exactly one transition on A, we have exactly one transition on B, so this is fine. Here we have exactly one transition on A, this is good, but we have two transitions on B, so this is not DFA. Now here we have exactly one transition on A and B from Q1, exactly one transition from A and B from Q2. We don't have any final state, but this is not the requirement for DFA, so this is DFA. Here also we have exactly one transition on A and B from X, exactly one transition of A and B from Y, so this is DFA, and we have final states X and Y. Here we have A and B from X, we have A and B from Y. We don't have any transition between X and Y, so this is not the requirement for DFA. And these four are, so this is also a DFA. So let's come to, like, there are a few points related to DFA. So every DFA represents one language. So suppose we have this DFA that we just constructed. So this is the DFA. So every DFA will represent one language. So set of all strings accepted by DFA known as the language equivalent of the DFA. So set of all strings that this DFA will accept, so that is called as the language of the DFA. So how we can find that some strings are accepted or rejected by this automata? So suppose we have this automata, Q0 is initial state, Q1 is final state. We have this transition. We have exactly one transition on A and B from each state. Now let's find out if A, B, B is accepted by this automata or not. So first we'll take A, and we always start from Q0. So we are at state Q0 because this is the initial state. On reading input A, we go to Q1. Okay, and then from there we will read B, so we will again go to Q0, then again we read B, so B comes to Q0. So after reading all these string, if we come to final state, then this string is accepted by this automata, and if it comes to any non-final state, then this string will be rejected by the automata. So we saw that on going from like A, B, and then again B, it comes to non-final state. The final state is Q1 only, so this is rejected by the automata, this automata. So suppose our input string is AA, so again we are at the initial state Q0. On reading A, we will go to here Q1, and then again on reading A, we will be at the Q1. So Q1 is the final state. So after reading this string, we are at Q1, and this is the final state. So this string is accepted by this automata. So this is how we find that if a string is accepted by DFA or not.